All right, this is Robert Needing, and I am back with another video for our Math 068 course. So we're going to start with section 13, which is finding p-values through randomized distributions. And we're going to talk about what to do with the data that we have. Well, first of all, a couple of things that I like to talk about in this first paragraph here that are important to us and understand what we're doing. So first of all, it says these are bootstrapping procedures are what we're talking about here. And by bootstrapping, remember, we're going to the sample, and from the sample, we're regenerating more samples. We're constructing what we're going to refer to as a sampling distribution. And that sampling distribution can use to make an inference about a population. That's our goal, is to look at the data, talk about it, resample it, make some kind of inference about its spread and the nature of what happens to it. Here's a nice statement that's going to be given to you. A couple things. One, first of all, when we construct, we are given that the null hypothesis is true. The thing that says nothing is going on is accurate. It is true, and we have no reason to believe that normalcy is not inferred. I'm sure this will pop up on a test. The randomized distribution will be centered on the value that makes the null hypothesis true. When we distribute the values and we create our curve and we put our dot plot together, we are going to see the null hypothesis centered in the middle. When we are working on this randomized distribution in StatKey, we'll be working on the right-hand side of StatKey. So far we've worked on the left and we've worked on the middle, but now we're going to work over here on this side over here, the right-hand side. It's important to know that we look over here for randomized hypotheses tests. So first thing we now have to do is review a little bit about our notation. And we've gone over this a multitude of times, so I pre-filled it out for us. If we're talking about a single mean, then it's a mu value, and its sample statistic is x bar. But yet at the same time, if we have a single proportion, p, its sample statistic is p hat. Remember, both of these are very highly correlated, but one talks about the population parameter and one talks about the sample statistic. If we have a difference in means, it's important that we keep the order, first minus second. If we're given the order, great. If we're not, then it's the order in which they come to us in the problem. Same goes for the proportions. And then my last one, my favorite, correlation coefficients of rho. I'm not really good at the rho symbol, the Greek symbol for rho, but I did my best there. It's just as acceptable, right? RHO. And our sample statistic for that is an R value. And remember, we've seen an R value when we calculate a y equal mx plus b or a y equal a plus bx. If we talk about moving into this area, what we're talking about is having a page that looks similar to this. And I think the best for me from this point forward in this chapter is to switch over and go to actual StatKey. So I'm going to jump into StatKey. And again, from the StatKey, we'll go over here to the right. Let's just pick single mean. And in single mean, we have three different distinct areas. The center will be our randomized dot plot, which you don't see yet. Notice it says the null hypothesis is 98.6. Mu equals 98.6. This is the null. Nothing going on. Now, this is the randomized dot plot, though, for x bar. Remember, when you have a mu population and you're distributing a dot plot, it's going to distribute samples of x bar. Where are those samples of x bar going to come from? Well, they're going to come from randomized samples. Where are the randomized samples going to come from? They're going to come from the original sample data. The original sample data for us has 50 things in it. Original sample data is right here. And it has 50 items. 98.26 is the mean. It has a median of 98.2 and a standard deviation of 0.765. Okay, so we can see those pretty clearly, pretty quickly. I'm going to erase this, get it out of our way. So first thing I'm going to do is I'm going to generate a sample. I'm going to go up here into this 50. I'm going to shake them up, and I'm going to get a average down here. So I'm going to go up here to generate one, and boom, there it is. Notice I did not get a 98.26 mean. I got a 98.528 mean. That was 50 things taken, and of those 50 things, I received a sampling of 98.528. That data just went right here. If I do it again, I generate another sample. It changed, 98.478. Notice now, I've got 98.478. If I jump between these, the data on the right side changes. Okay, well, we could sit here and we could do this for a very long time, and we could keep checking this. But what I want to do is I want to run about 1,000 of these right now. So I'm going to hit generate 1,000. So that process just happened 1,000 times, and here they all are. Notice that my null center is 98.6. If for some reason I needed to change that null hypothesis, let's say that the problem said, hey, the null is 98.4. I would click on 98.6. I would change it to 98.4, and I would hit enter, and my null center, I'd have to regenerate again. Now it's 98.4. So you want to change your null before you run your data. Okay. Now, so if we look back at our tabling, at our book of where we are here, let's go back to where we are here. Now that we have something run and we've done a couple of data values and we've changed our null right here, we've done all of those things really nicely. We've generated some samples. Again, note that our original sample happens in the top right-hand corner. We see that here in our slide. Our sampling data happened here, and then that data average went over here into the randomized dot plot for the null. The null is the center. Now let's do something with that. Now let's talk about the tailing. Well, the tailing, I'm going to go back to my Stecky. The tailing will change if we believe we are less than the null, greater than the null, or we don't care as long as we're one of those things from the null. For instance, if I left tail the design, notice that it makes in red everything which is smaller than 98.198. Left tails are things which are less than the null. If I change it from left to right, right is greater than the null. So therefore, the accommodating value for something which is looking at a right tail is really talking about something which is greater than the null by some measure of error. You should be picking up on words I'm using right now. If I go to a two-tail, I don't care if it's smaller. I don't care if it's bigger. I just care that it's a certain measurement of error away from, again, the null center. Left tail, less. Right tail, more. Two-tail, less or greater. So if we go back to our discussion here, and we start to talk about what we're doing here. So if I'm going to talk about the tailing, what's going on here, I have a couple of different things, and I have to be able to pick out these things. How am I going to know left tail, right tail? How am I going to know two tail? Okay, well, it all comes from the symbols that we are given. First of all, the null H of O is always just simply the center. This is the center. This is what it is centered up around, the null hypothesis. You want to measure an alternative which is greater. You want to know, when is this value greater? Well, on that example I just gave you, greater means to the right. We're really looking for this to take place on some distribution with a 0.7. When are you greater than some value? This is a right tail test. If I look at example B is exactly the opposite. Again, I really think that a picture is helpful, even just a fast sketch of the situation. My null center is at 10. My alternative says, hey, I want you to be smaller than 10. Okay, well, again, I don't know what that number is yet, but I'm looking for a left tail test. I'm testing left because I want to see the things which are smaller than 10 by some measurement of error. Again, remember that ME value is happening right here. If I go down to letter C, I'm at a equal position. Okay, well, that's important to know. Okay, what does that mean? There's no number there. Well, remember, if I do a little quick algebra here, mu1 minus mu2 is going to equal 0. So my center is at 0. Okay, is this a left tail or a right tail? This is a I don't care tail. This is a I'm not equal to your number. I don't care if you're left. I don't care if you're right. I just care that you're not equal. This is a two-tail test. Again, same deal on D. P1 minus P2 is going to be equal to 0. So when I draw my curve and I try to figure out my tailing going on here, again, my center is at 0. This one is not a not equal. This is a greater. I want P1 to be greater than P2. This is a greater than. And a greater than symbol means that I'm dealing with a right tail test. You figure out the tailing of your computer test based on the information that you have in front of you as far as the symbol, less than, greater than. So when I look at editing a box for an axis to match an observed statistic, so what you'll notice what it says here is that, okay, we have a statistic here. This is my statistic value right here. And it says change the default value by clicking on 98.392 to enter a statistic from the original data. Okay, so what we want to do is we want to change a value. So I'm going to go to Stat Key. And I'm going to go here, and my data is a little bit different because of what I ran, because remember, data is always slightly different. But what they're asking us to do is to come down here and change this number. Sorry that keeps getting in your way right there. I'm going to click the 98.19, and notice that this number up here is 0.025. I'm going to click this number. I'm going to change it to 98.2. I just changed that statistic. This is the statistic I am changing. And that statistic, notice that this value up here changed. Most important thing for you to note right at this particular place here is that this number that I'm dealing with right here that I'm seeing, this is my p-value. And the p-value will change based on the statistic. As I change the stat, the p-value changes itself. I'll do that again one more time for you. As I change the stat, so I'm going to move the stat up to 98.25. In essence, I'm changing the cutoff, and the p-value accordingly changed to 0.086. As this p-value goes, or as this value, the stat goes to the right closer, it's going to get more dots. As it gets more dots, the p-value is going to increase. As this number changes, I'll make it 98.1. I'll move it way out to the left. Notice how small the p-value got. It got so small, we don't even have a value sitting in there because there are no numbers which are less than that number. Stat on the bottom, p-value on the top. Now, I can also change the p-value. I can click on here and say, hey, I want the p-value to be 0.005. It will change the p-value and say, hey, this is the stat that goes with this particular p-value. Very important nature of what we're doing. You can see all the associations here. It says the p-value is 2 times 0.0024. Okay, well, what do they mean by that? Well, if you look at that statistical value, if I have a two-tailed test, there are 0.005 things on the left, and there are 0.005 things on the right. So if I am dealing with a not one tail, but a two tail, then the p-value is equal to 2 times, we say, the smaller one, although generally they always equal each other. So in my case, it's going to be 2 times 0.005, and we're going to wind up with a p-value of 0.01. P-value will be incredibly important to us in the upcoming chapters. StatKey does an excellent job of finding the p-value for you right on the computer. Remember, the p-value is always up here. And if it's a two-tail, it's 2 times what you see on any one given end. If it's just simply a one-tail, then you won't have to worry about that. It talks in Stackey, it says the null and alternative hypotheses and samplings are given. So we're given a value of p data to be p hat 1 is 24 over 30 at 0.8, and the other one is 14 over top of 20 to be 0.7. So I'm going to show you how to make that change. So this is two proportions. We're going to go to our stat key. I'm going to go back to stat key. I got to first of all switch out of here. Give me 1 second real fast. So I'm going to go back over to my randomized hypotheses. I am going to go down to where it says difference in proportions, because that's what we were given. In the difference in proportion values, you can notice you have a couple of different things here, but I have an edit data, top, edit data. Our first number was 24 out of 30. Our second number was 14 out of 20. I'm going to say, okay. I'm going to generate 1,000 samples. And when I generate those 1,000 samples, you can see all of the data that has occurred, not only from the original 0.8, 0.7, and the difference is 0.1, but you can also see that in this particular randomization sample, I got a 0.183. If I want to create a two-tailed test out of this, as the book indicates we should do, because when I look at that, notice the not equal. This is how I know that I'm doing a two-tailed test because of that not equal. It won't come out to us and it won't tell us that. It will assume that we are going to look back at it. So I'm going to go back. I'm going to turn it into a two-tailed test. And right away, I see a sample statistic of 233, another one of 267, and I see a 0.025. Remember that the p-value is not 0.025, it's 0.025 times 2 to give us both sides because it's a two-tailed test. So it's really, it really is what we see, but it's on two different sides. I would recommend that you go into Stackey, you try some of the sampling, you play with the left tail and the right tail, and you look at the p-values, and you see how they change based on changing the coordinate at the bottom. Remember, the coordinate at the bottom is referred to as the statistic.